All right, let's take our understanding of Coulomb's law, this equation right here, right, where you have the charges, the multiplication of the two charges directly proportional to the force, and the distance between your charges is inversely proportional to the force. That is, the distance between squared is inversely proportional to the force. Q's charge, R distance between, K Coulomb's constant. That's a constant you look up in the book or in your packet, 9.0 times 10 to the ninth Newton meter squared per Coulomb. And you get a force between them in newtons, of course. Let's take that into two dimensions, though, away from our little one-dimensional simplistic problems here. Just thinking this through. First, before I talk about this, this is an actual force, meaning that we can actually put that into any force diagram. Once again, you'd want to draw free body diagrams of these objects. For example, here, I have some positive charge and a positive plate. And if this were on Earth, right, I would have a force of gravity pulling down, Fg, pulling downwards. And because opposites repel, right, I've got a positive plate, positive charge, opposites repel. Since the plate's nice and wide here, we could assume that the electrical force electrical, is going up, right? And so a free body diagram of these things would look something like this, right? I'd have Fg going down if this was flat and on Earth's surface, and I'd have force electric going up. And then I could go through my standard sum of the forces equals ma, right? And if I called up positive and down negative, now I'd have Fe minus Fg equals ma, right? Just for the sake of this argument, to kind of keep in the idea of the oil drop experiment that we're going to go into later, let's assume that these were balanced, right? So it's an equilibrium, right? So acceleration is 0 now. And then I would have two equations. Now, you know the equation for this side becomes 0. You know the equation for force of gravity. Force of gravity breaks into mg. So then my next line, this would be equals 0, and this becomes mg, excuse me for writing over my other plus sign that went with my y-axis. So that minus, but now I have an equation for electrical force, right? K, Q1, Q2 over R squared, right? And you just plug that equation in. And so now, just using all the other knowledge that you've had, just using Newton's second law, summing up the forces equals ma, I can actually write an equation that involves electrical force. It's just another type of force. And any type of force can go into Newton's second law. Now, the electrical force, or Coulomb's law here, that force sometimes interacts with other types of forces, right, where you're summing up forces, F equals ma, and you're coming out with, some of the forces where you have some other macroscopic forces you have dealt with, tension, gravity, other things like that that you've already dealt with in Newton's second law, and electrical force just goes in there with it as a type. But it is very rare that you find that. For the most part, electrical force is going to exist solely by itself, right, with other electrical forces, not acting on a large macroscopic scale. In fact, the number one application that you're going to find, unless you purposefully set it up to where it's interacting, the number one application, not number one, but a large application that you find is in chemistry, with bonds and bond length. In fact, there's an entire course pretty much dedicated to this and many other ideas of chemistry called P-Chem, or physical chemistry, upper level chemistry class in college. And this is the basis, the real rock bottom foundation of this idea of physical chemistry here, is Coulomb's law with bonds between things. So here I have a water molecule, oxygen, two hydrogens. We know from X-ray analysis the angle between the two hydrogens. We also know the bond length, how far apart the two nuclei are. So both of these, since it's a perfectly bent molecule, both of these bond lengths is 0.9584 angstroms, right? So now if you think about this, you can calculate water is a polar molecule here. So that means water, for the most part, the oxygen atom ends up somewhere around -2. Not all the time, right? The electrons are going back and forth, but the oxygen likes to take them on more. So for approximations for our class, we'll just say, almost like it's ionic, it takes on both electrons, and the hydrogens are left at +1. Now, that's not always true. They're sharing the electrons, but just for the sake of calculation and not having to deal with more complex issues, let's just start there. If you think this through now, I've got a couple of forces acting, right? So if I put this oxygen atom, let's say, on an XY plane here, so let's kind of draw an XY plane on this, I've got a force acting, opposites attract. I have a force acting this way, force 1, and I have a force acting this way, force 2, right? And the sum of those two forces, right, the force, the hydrogen attracting the oxygen molecule, H1, if you will, attracting it this way, and the other force attracting it that way, the sum of those two forces is what will give me my net force, which should be right in between, right, F net, or sum of my forces. So as you can see, all you're doing here is you're just summing up the forces equals ma, or if we're just looking for F net, total force, it's a vector, it's just adding your vectors, adding your two force vectors, like we did way back at the very beginning of Newton's second law, really all the way back to vectors. Here, just adding vectors where you know the forces, right, F1, F2, come from this equation over here. Water is a polar molecule, meaning that this positive hydrogen would be attracted on this molecule to that negative oxygen there. And so now I have a length between them, right? And a overall charge if we assume that the polarity, the electrons like to stay with the oxygen. I also have, if you think about it, on a straight line here, an oxygen and a hydrogen, and they're sharing an electron. If we zoom in on that, right, I have a hydrogen nucleus, I have an oxygen nucleus, and an electron in the center. Now, this is a very bad idea, and anybody who's taken physical chemistry is going to be jumping up and down screaming at this idea, but to neglect the electron shielding, we haven't talked about being able to calculate that, and to not have to use electronegativity is what you should be using, and here to take into account the electron shielding, because oxygen, the nucleus, has eight protons in it, but it's not all 8 protons attracting one electron. There are other electrons around the oxygen atom that shield some of that charge from this electron. But let's pretend we stripped away all the other electrons. That would leave hydrogen with a +1, oxygen with a +8, an electron between them. And if you think about the forces on the electron, right, I'm going to have a very large force attracting it to the oxygen, we'll call that FO, and a much smaller force attracting it to the hydrogen. Right, and so the electron, just from that logic right there, should live the vast majority of the time over with the oxygen molecule, aka the polar, making it polar, leaving hydrogen more positive, oxygen more negative. All right, work a couple of problems for you. First one, we're just going to deal with things in a nice line here. So I've got an O2 molecule, the molecule that you breathe in that allows you to live, right? I have 2 oxygens here. We're going to use that same bad assumption, forgetting electronegativity, stripping away all the other electrons, only dealing with one. This is a covalent bond, right? So it's sharing this electron. Bond length between these two, we know, is 121 picometers on average, I should say. And I'm going to take my electron right now, one of the 4 electrons that it shares, and the only one we're going to deal with right here. We're going to say that it is 47 picometers from this oxygen on the left, which I am calling number 2, and the oxygen on the right I am calling number 1. Now, I'm going to have 2 forces on this electron. Number 1 is going to be pulling a little bit this way, and number 2 is going to be pulling a lot harder that way, right? Because it's closer over there to the second oxygen molecule, thus it's going to have a lot greater force. Free body diagram of that looks something along these lines over here. So if I'm looking for the net force on this electron, all I need to do is add up all my forces. F net, or the sum of the forces, and I'm not doing sum of the forces equals ma. I'm not solving for the acceleration in this problem. I could sum up all the forces equals ma. I know the mass of the electron, but here I'm not necessarily worried about that. I just want to find what is the net force on this electron in the center. You could do the same to figure out the net force on the oxygens on the outside. I have 2 forces, right? I'm going to have F1 and F2, and let's call this way positive and that way negative. Don't forget, whenever you're doing Newton's second law problems, free body diagrams, or adding up vectors, you have to choose positive and negative. So I'm going to have F net is going to be whatever F1 plus F2 is, right? So F1 plus F2. Now, and excuse me, that shouldn't be plus, that should be minus F2 there, because F2 is going the negative direction. Now, F net, I know the equation for F1, F2. It's just Coulomb's law. And now we need to substitute in our charges and our distances. Remember, the charges come from the electrons and the protons in this problem. Other problems, maybe it will actually just tell you what the charge is. It's 6.5 microcoulombs for charge 1, and the middle charge has 7.3 microcoulombs. But here I'm going to get it from the base charge of an electron-proton, 1.6 times 10 to the negative 19th coulombs, multiplied by however many protons or electrons I have that I'm dealing with. And for space requirements, I ended up not putting in my 1 times 10 to the 1.6 times 10 to the negative 19th for the elementary charge, charge of a proton, charge of an electron here. I just use E. So everywhere you see an E, 1.6 times 10 to the negative 19th, because that's the charge of a proton electron. So I have K, charge of my electron, I'm calling charge 1, and then charge of the first oxygen atom, this one over here, because we're dealing with F1. Right, 8 times the charge of a proton, 1.6 times 10 to the negative 19th. Notice I did not make the charge of the electron negative. I left it positive because I have dealt with directions manually in my free body diagram, calling to the right positive, to the left negative here. The distance between this electron and this first oxygen is 121 picometers, this distance, pico times 10 to the negative 12th, minus 47 picometers. That's what this distance right here is, right? So there's my 121 times 10 to the negative 12th minus 47 times 10 to the negative 12th. That R is squared, right? Minus now force 2. All right, so K, charge of the electron, charge of the other oxygen nucleus, 8 times the number, or 8 times the charge of a proton, divided by the distance between them, 47 picometers, 10 to the negative 12th, squared. So now I just punch all that into my calculator. So I come out with a net force of negative 5 times 10 to the negative 7th newtons with sig figs because of my 47 picometers to sig figs. Technically it was negative 4.978 blah, 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 times 10 to the negative 7th. So negative 5.0. Negative because I called to the left negative, and that's where this electron is going to be experiencing the force going that way. Let me also point out what I did with these picometers here in case you missed it. All I did was drop the pico and put on times 10 to the negative 12th, because that is exactly what pico means. Every time I see a picometers, I just take whatever the number is and stick it times 10 to the negative 12th. Now, this is not correct scientific notation, but your calculator does not care, and whenever you punch it all the way through, you come out with something in correct scientific notation, so no need to waste the time actually converting these into correct scientific notation there. All right, if you felt completely comfortable with the previous problem, you'll probably be okay to skip this one. But if some things were a little, you weren't completely sure of what was going on, check out this problem too. I'm going to work this one rather quickly. I have 3 charges, 2 of them positive, 2 of them negative, and I'm going to look for the net force on this one. Once again, I'm not solving for the acceleration. If I did want to solve for the acceleration, it'd be very easy. I'd set whatever my net force that I find, I'd set that equal to ma, right? But this is static, so I'm not worrying about them accelerating like they're fixed in place. So I have 3 forces. I'm looking for his net force. So let's draw a free body diagram. So I have a positive here, negative there. That means there's a force attracting, right, this guy over towards my negative, which I called charge number 1. So my free body, force 1 pulling to the right, which I'm calling positive. And here's a positive, positive, right? And so this guy is trying to push him to the left. And we're carrying this free body diagram here is about the one that I'm caring about. What's the net force on him? That's something students sometimes get confused about, is what do I do my free body for? Well, you're doing it for the charge that you care about. And you could do it for any of these charges. All of these would have different net forces being exerted by the 2, let's say, that you aren't caring about, the 2 that are exerting the force. So since we care about him, these 2 are exerting the force. I got F1 positive, F2 negative, pushing back the other way. So sum of my forces, or the net force, and I guess I shouldn't have that sum sign since I wrote F net, is F1 minus F2. So now I've substituted my numbers, right? K here is 9 times 10 to the 9th, right? That's just a constant. Q1, Q2. Now, let me talk about Q1, Q2. This is the charge exerting the force, if you will, and the charge that's having the force exerted on. If you get those 2 backwards, that doesn't matter. So don't think that this Q2 applies, the same 1 and 2 here. So I'm dealing with the force that 1 is exerting on this guy. So here I've got this charge, the one doing the exerting, 12 times 10 to the negative 6. Notice the lack of negative sign there. Reason that I didn't include the negative sign is because I've already dealt with positive and negative on my free body diagram. So just 12 times 10 to the negative 6, this charge 1, and he is exerting his force on 17 times 10 to the negative 6. So that's the force that charge 1 would exert, distance of 32 centimeters. They're squared. And then over here, force 2, so the force that he is exerting on the one that I'm carrying about, the net force on him, I have K. I have his charge, 23 micro times 10 to the negative 6. Once again, whenever I see some prefix like micro, I just drop off the micro part and put in what it means. Calculator will take care of the rest. And then the charge that he is exerting it on, Q2, the charge that he is exerting on over here, 17 times 10 to the negative 6. And then the distance between them. I added up the two radiuses in between. We have to consider charges to be point charges, just like in Newtonian physics. With basic F equals ma, we had to consider that the masses were point masses. So same thing here, we just add up the distances, assuming these are infinitely small points. And now I can shove it in my calculator. And whenever I solve it all the way through, I come out with negative 4.1 newtons, meaning the repulsive force between these two positive charges, positive charge pushing him away, is actually greater because I called that direction negative. So the repulsive force between these two is greater than the attractive force between those two. And this was solving for F net on him. I could repeat the entire process and solve for F net on him, right? An attractive force this way and an attractive force that way, just drawing a free body diagram, adding up my forces to find F net. If the problem asked for the acceleration, then I could take whatever my F net is, right? That's sum of the forces, set this equal to ma, solve for the acceleration.